So after the introduction, we shall move on to the next topic, that is types of semiconductors. And in that, we have intrinsic semiconductor and extrinsic semiconductor. These are the two things we need to discuss in the types of semiconductors. Now, when it comes to intrinsic semiconductor, it is the pure semiconductor, or the as an example, the elemental semiconductor without any impurities. So you can take silicon or germanium, pure silicon block or pure germanium block. That itself can be said to be an intrinsic semiconductor. And the intrinsic semiconductor has equal number of holes and electrons. That's what we are claiming. So this, let us look in depth. Okay, so let us discuss deeply about it. So let me consider a silicon crystal and show you why these electrons and holes are equal in number. Fine. So just a moment. So a pure silicon, let us look at its crystal structure. So you have silicon atoms, and as you know, fourth group elements possess this property of catenation, due to which they can form very long chains. So each silicon can form covalent bonds with the neighboring silicon atoms. Like that, it keeps going. Now let me show the bonds between silicon atoms, the covalent bonds, this way. So this bonding extends, okay, into a very long chain, which we are not showing here. But I hope you can understand. So these are the covalent bonds which I am trying to show you here. And they try to provide the octet configuration to all the silicon atoms. So typically, since every silicon forms a covalent bond with another silicon, the outer shell of each silicon has 8 electrons, so it is stable. It attains stability. So like this, you have every silicon attaining an octet configuration, because it has 4 electrons in its outermost shell. When each silicon forms 4 covalent bonds with 4 other neighboring silicons, so it gets 8 electrons in the outermost shell, and that means the silicon becomes stable. So this is what we are trying to show here. Now what happens is that when we are at 0 Kelvin, all the silicon atoms will have this octet configuration, and there will be no electron which is free. All the electrons will be bound by the nuclei. Now what happens is, as the temperature rises from 0 Kelvin to something positive, some higher temperature, as you very well know, in these semiconductors, you have a valence band and a conduction band, and so if we think that above is conduction band, below is valence band, and the energy gap, which is around 1.2 electron volt, or something less than 3 electron volt. Okay, so like energy gap which is less than 3 electron volt. Now what happens at 0 Kelvin, all the electrons will be in the valence band. But as temperature rises due to thermal agitations, the electrons get more and more energy, and some of the electrons, due to the collisions amongst the electrons, may rise to a high energy, and they may jump from valence band to conduction band. So if I have to show the same thing in the crystal lattice, we can say that an electron somewhere here jumps into an open space wherein it is not controlled by nuclei. It is controlled by the overall electric field and all, by all the nuclei, but it is not bound to any particular nuclei. It can freely roam around. That is basically the conduction band electron. Now, this process of an electron jumping from valence band to conduction band not only creates an electron in the conduction band, but also it creates a hole in the valence band. So in the valence band, there is a hole there. Okay, that means absence of electron. Hole is nothing but absence of an electron. So an electron can come there and still the silicon atom will accommodate it. Okay, so the process of the electrons jumping from valence band to conduction band generates a hole in the valence band and an electron in the conduction band. So this is a very important thing that students must keep in mind, that when an electron jumps from valence band to conduction band, it generates a whole electron pair. That's what we should understand. Okay, hole will be a carrier in the valence band. Electron will be a carrier in the conduction band. So what do I mean by this? Let me explain to you. So what happens is that whenever you have a silicon block and if it has to conduct electricity, okay, electricity is flow of electrons, as all of you know. Now what happens is, if the silicon block has some holes, so there are silicon atoms there, okay, you have to understand. Now what happens, an electron is ready to come from the battery or outside, so that electron jumps here, okay, and it will fill this hole. Now what happens is that as soon as this hole gets filled, okay, this hole can again, this hole is getting filled means it is annihilation of whole electron pair. That means the whole electron pair is lost. Now, so the silicon got octet configuration, everything. Again, there will be agitations and a whole electron pair can be generated. Okay. So accordingly, what happens is that either in the neighborhood or the same hole which got electron can get rid of that electron, and that electron will jump into the next hole. And again, it can jump into the next hole, the next hole, next hole, next hole. Like that, finally the electron comes out. So an electron is given, an electron is taken. So that's how electron circulation takes place. And that is how current is conducted. Okay. So holes on their own can conduct electricity. Holes are current carriers in the valence band. And electrons in the conduction band, they're as good as the electrons that we see in conductors and all, because whether it is electrons in the conductors or in semiconductors, so long as they're in the conduction band, all that they do is they conduct electricity. So here everyone must understand that in the semiconductor, okay, at some temperature other than 0 Kelvin, we do have a hole in the valence band and a corresponding electron in the conduction band, and both of these individually or separately can conduct electricity. However, being their energy being quite low, valence band holes conduct electricity at much lower rate compared to the electrons in the conduction band. This is expressed using the parameter mobility. Hole mobility is quite small in comparison to the mobility of electrons. Hole mobility is quite small in comparison to that of the conduction band electrons. Okay. So I hope you are clear so far, and further we will discuss in the next video.